Good afternoon. My name is Steve Feiner, and it's a pleasure to welcome you to the session on visual feedback, or at least visual feedback 1, which means there's going to be additional visual feedback sessions. We have 4 great papers today. Our first paper is Looking into Attention Patterns in Extended Reality, an eye-tracking-based study. It'll be presented by Zhehan, who is a PhD student in the Department of Computer Science at Duke University, and he will introduce his fellow authors and give his talk.
Thank you for the introduction, Dr. Feiner. My name is Zhehan. I'm from Duke University I3T Lab, and are presenting the work that we work on with Ryleigh Bram, who's an undergrad researcher at the time, and Professor Maria Gorlatova, who's also here. And today our paper title is Looking into Attention Patterns in Extended Reality, an eye-tracking-based study. So nowadays it's getting more and more clear that AR can have test detrimental effects on users. Especially in the case of head-mounted pervasive AR, any effect can be more significant and hard to avoid both spatially and temporally. And when it comes to attention, we know as a matter of fact that AR might induce suboptimal attentional states. Things as flashy virtual objects, visual clutter, and obstruction of critical information can all lead to poor user experiences. And it's been shown in prior work that AR can lead to both distraction and attentional tunneling, which are kind of bad. So therefore, before AR gets widely deployed in our everyday life, we'll need to find a way to evaluate this potential degradation of quality of experience so that we can work towards safer and more effective experiences in AR. These days, VR simulations of AR has emerged as not only a testing platform, but also a way to learn about where the app can be beneficial and how the users behave when using the app. There are several advantages of this approach in that it can provide fully controlled environments, has fewer hardware limitations, and can provide access to various different environments. Yet, despite these advantages it offers, VR simulations nowadays are still a bit far from being perfect. The display of color and transparency is still not that realistic. In many cases, the interaction within a VR headset still relies on controllers to be accurate, and the hardware differences about things like field of view and computational power all contribute to this gap between the virtual and the real audio augmented world. With these concerns, we really want to ask ourselves the following question: do we trust VR simulations to accurately replicate user behavior in AR? So this question leads us to this work on looking into human attention in extended reality. In this work, we developed a Sudoku solving app in both AR and VR that contains both guidance and distractions, which is found engaging by about 95% of the 38 users we recruited into user studies. And using the eye tracking data collected in those studies, we compared attention patterns in AR and VR and found that VR induced higher perceptual load and decreased user focus, while in AR, there's an opposite trend of increasing cognitive load and promoting higher level of focus. We also trained machine learning models to predict the existence of distractors and the user's attention control ability, and found that model performance dropped significantly when being transferred between AR and VR, which further validates the gap between the two medium. So I'll start introducing the Sudoku solver app that we built as the task to investigate user attention. This app was built on a Magic Leap 2, which provides us with like 60 Hz eye tracking of both eyes and access to the camera feed. We chose this task since it demands a sufficient amount of attention from the users, and it provides space for adding both guidance and potential distractors. As shown in this video, we implemented these visual hints in the form of blue and green overlaid rectangles on the puzzle, together with a form of audio hints where a man's voice would read out the digit to be filled in a specific cell in certain scenarios. These hints were generated by sending the image to a backend edge server that runs digit recognition and hint generation. On the distractor end, we put a Duke Blue Devil at the bottom right corner of the puzzle, which is normally dancing and sometimes shaking its head at you when you made a mistake. And additionally, the devil would randomly start to run around the puzzle board as a pure distractor. This design reflects the idea of branding of commercial apps and was displayed in a way that adds amusement to the experience with the potential possibility of being distracting. We also added common task-related, indirectly helpful elements, such as the progress bar and the timer to the app. To compare attention patterns in AR versus VR, we developed a VR version of the same app, implementing the same set of elements and logic. we'll build the app on an HP OmniStep headset, which offers 120 Hz eye tracking, also of both sides. There are several differences between the AR and the VR app in terms of interaction, given the difficulty of writing numbers in a cell accurately in VR. We use the controllers for selecting cells and digits. And in order to ensure that the controller interaction works smoothly, the puzzle was placed slightly further than an arm's length away from the user, within the diagonal angle of the puzzle being around 35 degrees. And also in VR, since we know all the digits that are put onto the puzzle, unlike in AR where another server is used, hint generation generally takes less time in VR than in AR. We do want to note that this simulation is not a pixel-to-pixel level perfect replication, yet at the current point of technology advancement, these disparities are still inevitable, which actually inspires us to this work. So using Sudoku apps we carried out 2 user studies for AR and VR, each with 19 disjoint participants. So in both studies, we collected users' attention control score with the flanker squared task, in which the participant's task is to select the response option with the central arrow that points in the same direction as the flanking arrows in the target stimulus. So each user would do this for 90 seconds, and we can collect their scores, and here the AR population and the VR population had relatively close attention control ability. After completing the task, user would go through 2 Sudoku solving tasks. First, a 3-minute unguiding session without any hint or distractor, and then followed by a 20-minute guided session where all the mentioned elements were added. Here are some general feedback about from the users towards the experience. A combined 95% of the users said they were fully occupied in the game. And as we expected, among all the virtual elements implemented, the visual and audio hints were found to be the most useful, and the mascot, or the blue devil, was found to be the least useful. And interestingly, the mascot running behavior was only found distracting by 26% AR users and 16% VR users, and even fewer of them found other elements, such as the timer or the progress bar, to be distracting. And we think that this was likely due to the users to be in a mode of flow, that they were able to navigate themselves through the task and ignore additional stimulus. And we will further discuss about this later in the presentation. So looking into attention patterns in AR and VR, we ran gaze-based analysis on the collected data by extracting gaze events, including fixations, saccades, and smooth pursuits. Additionally, we conducted region of interest-based analysis in which we defined 5 ROIs as the puzzle, the hints, the mascot, the progress bar, and the timer. And the metrics we considered were the proportion of fixated time, the mean fixation duration, and fixation rate. And we chose these metrics since, first of all, proportion of fixated time is known to review the level of focus, and so is how mean fixation duration is being interpreted. And on the other hand, fixation rate can reveal how often attention is redirected. And when combined, it's been shown that in prior work that increased MFD and decreased FR indicates increased cognitive load, while the opposite indicates increased perceptual load. So here's the major results in the comparison study. We extracted 5 periods out of each user session, including UG, the unguided session, UA, the whole period when they're using the app, and D, which is the no distraction period, where neither the mascot's running, nor the audio was played, and MR and AP being the periods when those 2 stimulus were presented. And first, if you compare the metrics of the same period between AR and VR, we found that in the UG period, AR had the lower MFD and higher FR than VR, but this trend was reversed when the app was used, that in AR, MFD became higher and FR became lower than in VR. If we focus on one media, we can see that in AR, when we compare UG with all other periods, there was an increase in MFD, decrease in FR, and increase in PFT. When in VR, we saw a decrease in MFD and increase in FR. So this suggests that while Sudoku solving task was originally less cognitively demanding, in reality than in VR, having the app running in AR led to increased cognitive load that surpassed VR, while the effect of VR was essentially the opposite. This actually informed us that having virtual and real fused in a task made it more cognitively demanding than a pure real or pure virtual task. Additionally, when we look specifically at fixations towards the mascot, we also found this difference between AR and VR, that in AR across all periods, the proportion was rather stable at 0.4%, when in VR, there's a significant increase from 0.3% to 1.5% when the devil was running. And further looking at individual attention controllability, we found a clear correlation between more fixation on the Duke Devil and lower attention control scores in AR, where those with below average ACS had 6.4 fixations on the muscle on average, comparing with 2.2 fixations for those above average group. This trend was not observed in VR, where the two groups were insignificantly different. So this told us that it's generally easier to distract users in VR than in AR, and that in AR, this more cognitively demanding nature of the augmented task served as a shield to distraction, making it less noticeable. Using the eye tracking data we collected, we also trained transformer-based machine learning models on 2 seconds of data. We performed 2 tasks, first to predict if the muscle was running, and second to predict the user's attention controllability. We chose the 2 tasks since they are both valuable for building apps that can adapt to attention-related features, either at task level or user level. Additionally, we tested whether there exists a domain gap between the 2 data sources of AR and VR by transferring models trained on one domain to another. We also, at the same time, explored pre-training on a public data set named gaze-based VR for its effect on domain transfer. Briefly speaking, we used different combinations of features, including gaze directions, eyes open amount, or gaze dilation, and gaze targets for the 2 tasks, and found that the model performed generally better on predicting ACS than MR. This can be attributed to the fact that the distractor was not powerful enough to induce more than marginal user responses, and the severe class imbalance issue also accounted for this result. Additionally, we transferred the ACS prediction model in both ways and found significant performance drop bidirectionally. We did find, however, that if the model has been pre-trained on gaze-based VR and fine-tuned on the AR dataset, it would suffer less from this domain transfer, but it's not observed on AR, likely because gaze-based VR is a VR dataset, and we probably need large-scale AR datasets to help adapting VR models to AR. Yeah, in conclusion, we built a Sudoku app in both AR and VR, conducted 2 user studies, and collected their attention control score and eye tracking data. We found the nature of having real and virtual context mixed in AR lead to increased cognitive load in VR, and we found that this gap between AR and VR was further validated by the results of machine learning models. Several limitations of this work. First of all, this task of solving Sudoku puzzles is primarily like mental effort, and will be helpful to investigate other tasks as well. And second, we have included audio as a stimuli in our system and found something interesting about it. But in this work, it's not been really fully carefully controlled, and we believe research on how audio could affect attention in AR can lead to important findings. Actually, we are currently doing this with another app built in the lab. And thirdly, the fact that we found the users to be not as distracted as we imagined calls for designs that substantially captures attention, and we are currently exploring ways of doing that by first, violating known good design principles, and second, try to fuse a real-world task with specially crafted virtual contents. And yeah, that's all for my presentation. I hope it's not too long, and I will welcome any questions.
Thank you very much. Do we have anyone with a question?
Yes, please.
Thanks for the talk. Really interesting work. So your overall conclusions about like the validity of AR simulation in VR, it seems like the VR condition that you had, you didn't really attempt to make it as close of as possible of a simulation of the real world task as you maybe could have. So did you think about making some of the virtual elements transparent and replicating the real world environment with 3D models and making sure that the interaction methods were the same? There's seems like there could be a lot of reasons why you found those differences that might not be inherently related to AR versus VR.
Right, thanks for the question. And yeah, we are aware that the current VR app is not really like a pixel-to-pixel level replication. And we are doing this mainly because in this task where you have to write digits in little cells, it's hard to do it with a controller, and that if you use VR very often, you might be able to do it, but for people who haven't really been used to this kind of interactions, just by writing things, they can have major differences. And also, we think most of all, for this task of solving puzzles, the nature of it wouldn't be changed very much by whether you're accompanied by a bookshelf or not on your somewhere in a room or not. But yeah, we are currently also thinking of replicating it in different ways. For example, instead of bringing VR to AR, we can bring AR to VR by using video see-through headsets, which can be a potential way of bridging the gap a little bit closer.
Okay, thank you. I think in the interest of moving on, we'll save additional questions for later. So our next paper is Textual Information Presentation in Virtual Museums, Exploring Environment, Object, and User-Based Approaches. The first author is Yuexin Yao, who's an undergraduate student at Zhehan, Liverpool University in China. However, because of visa issues, she couldn't be here, so instead the presenter is going to be Bingqing Chen, who's now standing up there at the front, who's a research assistant also at Zhehan, Liverpool. She'll introduce her, the two authors. Yes.
Sorry, bit nervous, first time for the academic conference. Okay. So good afternoon, everyone. My name is Bingqing Chen from University of Zhehan, Liverpool University, and I would like to share with you some of our research progresses on textual information presentation in virtual museum, exploring experiment, object, and user-based approaches. This work is an undergraduate dissertation of Yuexin Yao under the supervision of Dr. Yue Li. Due to visa issue, as Steven said, Yuexin couldn't make it to the conference, so I'm presenting this paper on her behalf. So imagine the physical museum. Textual description are typically displayed on placards or signage next to exhibits with a virtual museum within a virtual museum environment. As text descriptions can be presented in various ways, such as fixed in the virtual environment, attached to the exhibits, or held in user hands. So, however, the design space of artifact information presentation in virtual museums were underexplored. Virtual museums are gaining popularity, and artifact information is crucial to exhibitions, while textual descriptions remain the traditional method. They are typically crafted by professionals following guidelines that overlook user-centered perspectives, failing to address users' needs, particularly in key information dimensions. Current artifact guidelines primarily focus on content recommendations, but often neglect spatial layout, especially in virtual reality environments where design complexity is higher. Crafting effective textual information layouts in VR is particularly challenging due to this complexity and the lack of clear direction in existing guides. Additionally, there is little understanding of the relationships between artifact information dimensions and spatial layouts of information panels in virtual museum. Therefore, we propose three research questions. The first one is, how do users perceive the importance of various dimensions of artifact information? Following with, what are the expected displays of information panels in virtual museum? Do they prefer it show or hidden? And what are the relationships between artifact information dimensions and spatial layout types in virtual museums? Therefore, we designed a virtual museum environment for this study. The VR system comprises 6 scenes. Each scene consists of an artifact and multiple artifact information panels. In total, there were 59 information panels in the 6 tested scenes, including 6 names of artifact, 6 names of museum, 22 observable information, 17 non-observable information, and 8 interpretation information. So we introduced 6 spatial layouts that fall into 3 primary spatial layout approaches, including environment-based and user-based approaches. And environment includes wall and pedestal, which are fixed in the environment. Object-based, including top, side, and tooltips, which moved along with the artifact. And user-based means handheld move with user's body. Yeah. And here's a video illustration of the 3 different approaches. Yeah. Sorry about the order. Right. So afterwards, we conducted an experiment with 24 participants to explore user preference across 6 scenarios based on the different layout approaches. Participants were asked to evaluate the importance of artifact information and then enter the VR environment to review the text information panels and choose the ones they wanted to display and arrange their spatial layouts. Once they completed the panel setup, participants were asked to select and discuss which panels they would like to hide. After completing 6 sessions, they were asked to conduct a structured interview with 3 questions. So in response to our first research questions, we found that non-observable information, such as historical context, were perceived as most important by users. Moreover, user panels were rated of high importance. So for the second one, participants also preferred to display most information panels rather than to hide them. However, tooltips and handheld panels tend to be hidden. For the third one, in terms of information panel display preferences, we found that environment-based and object-based layouts were preferred over the user-based layout. Specifically, tooltips were favored for observable information, and wall panels were preferred for interpretation and museum names, and pedestral for artifact name. So in the interviews, participants shared that their decisions on panel layouts were mainly influenced by these 4 factors, including the dimensions of the panel's information, importance of artifact information, symmetry of layout, and length of the information. For example, they want the panel to be tidy, symmetric, and hope it to be tidy and neat, and they're more inclined to have long segments of text on the handheld panels. They also mentioned that for the second interview question, they also mentioned that longer descriptive texts were often preferred to be hidden initially. Also, in addition, for the third one, last one, most participants mentioned they prefer the object-based approach, which creates a strong link between information and artifacts. Also, they mentioned side and top layouts are simple, intuitive, and visually appealing, while wallpaper made the scene neat and tidy. So based on the results, we discussed our findings and provide design recommendations. The design space is presented in this figure, summarizing the insights from participants' spatial design results and interview comments. And you can see the dotted frame means they want this kind of information to be hidden, and the stars on the top left means they want it to be hidden by default. So for the environment-based layout, which the participants think this replicates the physical museum setting well and providing a familiar and intuitive experience. For the object-based layout, it builds strong connection between artifact and its information, enhancing interactivity and immersion. And last, for the user-based layout, it can help to reduce the information overload but need to be used less frequently. It making them more suitable for subjective or interpretation content. And that's all. Thank you for listening. Yeah, and if you have any question, please feel free to put your question on Discord or approach to Dr. Yue Li. Yeah. Thank you.
Okay, so we have plenty of time. Thank you very much for the talk and for a briefer talk than I thought it was going to be. So we do have time right now for questions. And do we have the person who's going to be answering the questions here? Okay, yes.
Oh, okay, sorry.
Hi, yeah, thanks for the presentation. I think it's a very interesting topic of how to display information, and I'm wondering, about the scalability of this, right? Because in a normal museum, you often have a lot of exhibits, meaning that this might maybe also influence the choice of how things are displayed. And I'm wondering whether you also have thought about this and maybe have some ideas whether maybe some of the preferences might change. Just if you have, for example, the wall, right?
Yeah.
As the most favored place for information. Now you have just not one exhibit, but maybe 10 in a very near vicinity.
Yeah.
Do you think that the wall would still be the preferred way?
Yeah, that's a good question because initially when we were designing the study, we were thinking about whether it should be a single display or it's actually populated with different objects in the same room. But it feels like that if we have multiple objects in the same room, it might interfere with participant decisions because you're introducing more variables in the study. And that's right, because when we scale the single object setting to a multi-object setting, there might be difference. But in the instruction to participants, we were particularly emphasizing that please focus on only one object only. And this is the purpose of the study is to compare the environment, object, and user-based approaches, but not really to design an entire exhibition room. So indeed, it's a limitation of the study, and this should be considered when it's generalized to the environment like level design, yes.
Oh, you do?
I think we're all hearing. Okay, now the distance is a bit larger, but everyone can hear better. I was just wondering whether you think it would also make a difference whether the site that the exhibit is in is maybe a historical place or more of a modern building, right? I mean, if you consider an old temple, for example, where there's just a bit more going on in the background behind, right? Maybe some historic wall paintings and other things. I guess also then maybe this might change. So I think this would also be an interesting thing to look into. Have you considered this as well?
Well, usually in museums, that's two different settings. So we are talking about artifact-based museums. Basically, it's a modern environment room with multiple historical artifacts in it. And if we were talking about a museum, like a site scale, like a historical site, each site would be quite different, right? So comparing temple and also a ruins would be different. So that's not comparable in my own opinion. So for this study, we're only focusing on the museum setting where we host different historical artifacts.
Okay, yeah, I guess that makes a lot of sense. Thank you.
Thank you. And I'll ask one quick question, as we still have another minute or so. And that's that looking at the paper, you were using a Quest 2 for this, which is, of course, not the greatest resolution. And text is one of those things for which resolution is really important. So I'm wondering if you think there might have been any difference in results if you were using something that was even better than a Quest 3, even better than a Vision Pro, literally you envision.
Right. So device is definitely an issue. And actually, the environment setting is more complex than we were when we were planning it because there are a lot of variables like the font, the size, and also the panel size and the distance. So we referred to previous studies about reading in VR. So there are a few studies that particularly looking at reading text in virtual environments. And we were referring those parameter settings in our study and try to maintain that the conditions are consistent in our study. And for the device in particular, there are quite a few high-end devices that are commercially available, but of a higher price. But considering the adoption in museums currently is mainly about the most prevalent ones, affordable ones like Quest. So that's why we adopted Quest for our study.
Okay, thank you.
Thank you.
Okay, so moving right along, our next paper is The Art of Timing, Effects of AR Guidance, Timing on Speed Control. It'll be presented by Jeroen Ceyssens, who's a PhD student from the Expertise Center for Digital Media at Hasselt University in Belgium. And he'll introduce his co-authors.
All right, I'm a bigger fan of holding the microphone. If it jitters a little bit, I'm a coffee addict, so just ignore that. So hi everyone, I'm here from Belgium, the Expertise Center for Digital Media. I'm going to be talking about the art of timing. Now, it's going to not say a lot right now. It's a bit of a catchy title that we chose, but I'm going to explain a little bit more about what this is about. So I know that all of us over here are researchers, and we probably look at a lot of activities like welding, caulking, gluing, painting. I don't know how much of you have actually ever done that over here. It's probably like something that you're not really used to seeing. But there's actually like a lot of important factors when you're doing these sorts of activities. Namely, you have the speed accuracy trade-off, as was mentioned yesterday as well in a lot of talks. But typically the feed rate actually decides also the speed that you're going to have to move at, because a lot of these activities require like a certain feed rate to be executed perfectly, and that means that you also have to adapt to do the correct speed in that moment. So we actually looked at one particular use case here, welding, and tried to adapt like our visualizations to do a study that would actually be able to translate over to more of these sorts of activities, where we actually focus primarily on communicating speed. Now, we actually have a ISMAR paper from last year that also explored this similar concept, and I have to quickly like talk about it because this goes further on this. So we actually looked there at the different types of instructions, like using like, faster, slower indicators, like a graph to show what the speed is compared to what the ideal is, and then like using an actual example of this is the speed and you can just follow it. Or we actually saw for like speed measurements where we tested like several different speeds, that the final one was actually the only one that was able to communicate speed. If you would tell people to go faster or slower, they actually don't really get the correct speed going, and they'll just be like, I'm not comfortable doing that. Well, if they see it, they will just do it anyways. So there was one big problem that meant us, that we actually had to do some additional research, namely that at the start of the activity, you actually have this huge jump in speed. That's because people are trying to catch up to that orb that's already moving, which means that you're actually doing like this entire part at the start completely wrong. So what do we actually explore now? And now the art of timing is going to start making sense very soon. So we looked at the welding activity here because the previous one was just a very simple pen and line activity. We wanted to kind of translate it over to an actual live activity and see how adaptable it is. So we actually are looking at very similar things. So right now we have like a Vive tracker. You have a real life welding torch. You also have a metal object, and we built a simulation of like the lighting and also the actual welding that's being performed with like the heat. It's also very interesting, if you know the orientation of the objects, you can actually just do this on anything that you want. So you can just practice the welding activity. We also do the welding reflection light that we also simulate to be able to get it as realistic as possible. Now, how did we build this activity? So we have a real-life welding torch that's actually connected up using some very simple electrical clamps. We then send a signal out to the welding torch, and funnily enough, when you press the button, it actually like closes the circuit, so you can actually detect perfectly when it's actually being pushed. So there we go, we have a haptic device. So to build the simulation itself, we use marching cubes, which allows you to kind of like make voxels where you can build up a grid, then decide with a lookup table like how you need to like simulate it. And for the heat, we kind of look at, okay, you're currently in this part of the grid. We can like build up heat in that moment that will dissipate to all the grid cells nearby. And then based on that, we can build the simulation and completely adapt it to whatever we want. We then actually just hide the object with a custom lighting shader to be able to then showcase only the light that is being reflected. And with AR Poster with the Vario, you get a welding simulation. Now, what is the study design that we actually did with this? So looking at the speed instruction of the like ghost orb that can just be followed along, we were kind of curious like how we were able to get that initial jump removed. So we looked at 4 different timings in an initial study, and we then did a second study where we also looked at how much information you actually receive visually. But I'll go more in detail on that later. So for the live instruction with prior, it's actually very simple. You have the actual example speed being shown. The welding simulation adapts itself perfectly for the speed that's being conducted, and we would then see on whether or not they would actually be trying to copy it correctly. Then with the during instruction, it's like very self-explanatory. You're actually like there, and the orb will move, and you will try to follow it. It's the same as what was originally in our previous paper. Then we also have the 2 combined, so we just show it beforehand. You can get a feel for what the speed will actually be like, and then you can actually try and copy it over during the activity. Then finally, we have merged, where we try to merge both of them together. The instruction will already appear from the left, so you kind of can get like a feel already beforehand, and then immediately like adapt to it, so we can maybe try and bridge that over. We did a between design study with 72 participants at a science fair, where we then actually saw for 4 different target speeds in a randomized order, like what actually would be the best. So the welding simulation completely adapts. So we wanted to eliminate that factor, because otherwise it's going to potentially cause issues with, oh, it's not going to weld at a particular moment if it's not the ideal speed. For the measures, we wanted to look at the speed difference, how far along the line it would actually be acquired, so when you're actually on the correct speed, how much overshoot, and also displacement and usability. For every measurement, we actually take the average of every single frame that's being captured, so that we can then like divide it up into millimeters of the line, so we can basically get an average result of that. So for the questions, we also use the welding torch as like a kind of a controller device to just indicate it, really to make it easy as well to answer the questions. Now, what do we actually find, first of all? When we're looking at the speed, it's actually very funny to see that for the merged instruction, the black one, you can actually see that it stays nicely on the actual speed, and you don't actually have much overshoot. Well, with the prior instruction, well, let's just say that people tend to really just stick to a comfortable speed around 4 centimeters per second, which seems to be like some sort of human, like, oh, I feel comfortable around this amount, because they don't really visually see it in that. For the position on the line where they actually receive the speed, actually the first is also merged, typically the like shortest, or only significance for the 8 centimeters per second. And then we also, for the overshoot, we found that merged indeed like significantly outperformed the other instructions. Prior was also very low, but that makes sense considering that, you know, if you're not reaching the target speed, you're probably not going to go over it as well. But there actually the instruction helped really well. For the displacement, we didn't see much displacement in general for the instruction. We saw only like a significance with all target speeds between the prior and the during. So that can like highlight some other importance. And then for the usability, there is actually a very interesting observation that made us want to do study 2, namely for the question of could you follow the speed, the prior instruction, everybody thought that they were perfectly on the correct speed when they were actually not doing it correctly at all. While the merge instruction, they were also actually very close, and they were actually really intending so. Also the visualization clear, they found the merge very clear, and also the prior, but merge was the only significant one. So some general takeaways from this. I'm gonna go over it fast because I don't want to like spend too much time as well. But in general, like the important thing that we saw was the efficient results were with merged, and prior really doesn't like convey that speed accurately, even though the people actually think it does. And we also noticed that with prior copy, it doesn't actually do much. Like they already have done the speed and everything, and then they're doing it like wrong anyways, and they're still gonna be surprised when it starts. So this is a little bit of a problem, because when you're a new welder, or any sort of activity that you're new to, you're gonna have an instructor telling you, hey, just copy what I'm doing right now, and then you're gonna do perfectly fine. But what our study actually kind of showcased is that we as humans have a very big problem understanding how fast something actually is. If I say you need to move like this, you're probably gonna have a hard time actually copying that movement. So we wanted to look at that in our second study. How much information do you actually receive from like seeing instructions beforehand? So we looked at the prior and the merged because they were at different positions, and we wanted to see what kind of way this would actually work. So what does this look like? So you have the prior hold, so people were kind of forced to stay in position while the instruction would move, and they were only allowed to start welding once the instruction actually finished. So this is kind of visual reference of this is the speed on top of the surface. Then we have the prior copy, where you actually are forced to copy the speed beforehand, and then gonna try to do it, because we wanted to see how much muscle memory you actually receive from this, from like doing the actual speed beforehand. Then for the merged hold, we actually have the merge instruction, but no live guidance. So the instruction comes from the left, you're supposed to continue it onwards, because we wanted to see is merge somehow working with, okay, you're moving it with your eyes, so because when you're following along with your eyes, you can maybe adapt faster. And then finally, with the merged copy, you actually are forced to copy the movement as well, and then we don't give live guidance, but you're already moving at the correct speed, we would assume. So maybe that would actually help you to do the activity correctly. So here we did a within subject design study because we wanted to get more understanding as well and get more feedback from the participants, where we actually did first 3 training lines at speeds 2, 5, and 8. So this was the minimum, the maximum, and also the middle. And then also 8 target speeds in randomized order in a game of guess the speed. So after they actually considered the welding, they would actually have to answer how fast do you think it was, the instruction, how fast did you think that you were, and also what do you think if you could stay on the line. So for the confusion matrix over here, we actually saw that people, as expected, had a horrible time actually guessing the correct speed. Only the slowest one were they actually really good at, but they had the best performance with the prior copy in terms of guessing. Where in the middle section, it's really kind of a blur. It's really hard to be able to see how much speed it actually was. But if people can't quantify, is still something different from movement. So when we're looking at the actual statistics, we saw that before the welding, for the cases where they actually had to copy it, they were indeed, having overshoot at the start. They were perfectly on the speed. And then the moment they start welding, that speed just slowly starts to dip towards that same comfortable 4 centimeters per second, where the guesses were sometimes not necessarily too far off, but they would actually be already moving slower than they intended. So what does this actually mean? So communicating speed beforehand is really a complex problem. It's something that we actually as humans are really just bad at. And when now live instructions are provided, comfort prevails. People just go to whatever they feel is comfortable. I'm doing a good job, so it's probably going to be fine, even when they're already moving correctly. Ideal results work with a transition like merged, so you can see it and immediately continue onwards. So the live guidance is really necessary. Now, important to note, this is a 2D kind of space that you're working in. It might be that speed is going to be hard to communicate for something 3D, and that's still something that we will have to look at in future work. So anyways, reach out to me if you have more questions, and I'm happy to answer them.
Thank you very much, Jeroen. And we have time for questions.
Hello, everyone. I'm Guanghan from Tohoku University, Japan. And the question that I want to ask is, I saw in your experiment you use 2 short iron blocks, right? So, what I'm wondering, if you use a longer one, much longer one, do you think there's gonna be a difference in your results, about the speed estimation or the way the participants follow it?
All right, thank you. Excellent question, actually. So as I mentioned previously, we had a previous paper that also looked into a very similar sort of activity with a line and communicating speed. And there we did one of 60 centimeters in total, where here we did 15 centimeters only. So, 15 is quite a shorter space. In the design decision, the reason why we did so was because we already noticed beforehand that all of the findings that we would have across the 60 were typically at the very beginning. As soon as they get into some sort of comfortable space of I'm going to stick to this movement that I'm doing, that would already be happening at the very first part. And the only thing that we saw is that in the end they will only get slower and slower, but usually they would kind of balance toward 4 centimeters per second. That's something we found in the previous paper already. Now we once again confirmed that for some reason we always just move to 4 centimeters per second comfortably. I don't understand why. But that's one of the reasons why we were okay, 15 centimeters is going to be plenty, because usually at the first 5 or so, we already have most of the results that we would want.
I see. Thank you.
Thanks. Long term from ATH Zurich. So I have a question about the task that itself. We are using a welding as a task, right? So my question is it possible, or have you also considered using real welding as a task? And because actually you are using the video see-through as the solution, and actually that also protects the user from the radiation of the welding generation, right?
Yes, thank you. That's a very good question. So originally I was actually planning on making some sort of smart welding helmet for real life activities. And then I realized that with GDPR and everything, it was going to be really hard to do a controlled study with novices where we actually can be sure that it's going to be fully safe as well. So we wanted to be able to have it that the simulation as closely represents like the real life use case, so we can then like get the findings like that, so we can inform, oh, if you have like a very smart welding helmet in the future for experts, then we can actually already know what is the ideal instructions for it. We considered it, but it was going to be very hard to do the study in a very safe manner.
Okay, thank you very much, Jeroen. And we're getting ready for our last but not least final paper. Okay, and so our last paper is Annotations for Assisting with Decision-Making and Time-Critical Tasking. It'll be presented by Jamie Gower, who's a PhD student at the Australian Research Centre for Interactive and Virtual Environments at the University of South Australia. And he will present his paper and tell us his co-authors.
Okay, hello, my name is Jamie Gower. So my research is interested in using augmented reality to assist with performance and decision making in time-critical tasks. So while AR has been previously used pretty extensively, and there's a lot of research that has used AR annotations throughout various fields, generally they use them in procedural non-time critical tasks. However, environments do exist that are time critical and do require rapid decision making. Military tasking environments are one such example of these type of environments. Within those spaces, command and control centers are often used to support decision processing by providing information, gathering information, and analyzing information. However, these decision support environments are often limited by physical support infrastructure and limited display space, and typically can't be modified. So AR is a great tool to alleviate this, as we can use AR to provide further decision support while also being able to modify the decision support provided through it without having to modify underlying existing infrastructure. So we conducted 2 previous studies. So the first study looked at comparing AR supplemented displays to traditional displays for supporting performance and decision making in collaborative time critical tasks. For that study, we found that AR supplemented displays were a suitable alternative to traditional displays. Following this, we decided to further investigate by comparing the AR supplemented display with and without AR annotations. In this case, we used sticky note annotations and only sticky note annotations for the task itself. We found that the sticky note annotations that we used made participants feel more confident in their decision making and made them feel more informed about their decisions, as well as improving their feelings of collaboration. Further to this, we wanted to, while these studies produce meaningful results, the second study, as mentioned, only used sticky notes, which was one type of annotation. So we wanted to further this research by looking at different types of annotations and how they are affected by the time-critical environments and whether they are useful for supporting decision-making. So this research, as mentioned, aims to extend the research by providing an evaluation of several AR annotations which have been previously used in other research, and providing considerations when designing the annotations or using the annotations, as well as determining which ones are the most beneficial. As mentioned, several annotations were chosen from annotations that exist in previous literature. These annotations were sticky notes, animations, highlights, and icons. So sticky notes conveys information via text, animation display conveys information via a little animation. Sorry, I don't have a video of that. Highlights conveys information via a spherical object that represented a highlight, and icons conveys information with simple icons. So the annotations that we had, we considered them as existing on a abstraction spectrum. So from least to most abstract was animations, as they explicitly detail tasking steps to the user. Following that, we have sticky notes, which still are pretty explicit in detailing tasking information, but not as detailed as our animations. And then further along, we have icons, which were just like symbology of the tasking environment, so they were less explicit than both animations and sticky notes. And then finally, we have highlights, which were very vague but attention-grabbing annotations. And then on top of these, we had a control which contained no annotations as well. So the tasks that we used and designed for this attempted to model a high-pressure, time-critical tasking environment, military tasking environment. So we used StarCraft 2, as you can see on the screen there, to create this environment, and we made sure that we had tasks that were analogous to military tasking requirements. So the task goals for the task itself were to eliminate hostiles while avoiding casualties, and there were other goals such as rescuing allied forces, collecting relics, or in this case, ordnance, and a reactionary defend task. So completing the rescue and relic task helped assist with users performing the effective hostile elimination task. I'll just make a note here. So the annotations were used for these pink discs were considered areas of interest. So when a user gazed at one of these areas of interest, an annotation would spawn and be there for a few seconds so they could see what was at that area of interest. The annotated map reflects what the user would be seeing in the game screen for StarCraft. So that's an actual representation of the StarCraft map that was used. Okay, and the measures for this study were eliminations, casualties, enemies engaged, threat levels engaged, hostile groups engaged, the elimination to casualty ratio, which we call EC in this case, and completion times for the performance metrics. The subjective metrics that we used that we looked at were situational awareness, decision-making, perceived time pressure, memory recall, information conveyance, and annotation preference. We used a mixture of a semi-structured interview for these and also some questionnaires between each of the conditions. So the study that was conducted consisted of 26 participants. It was a within subject study. The participants had minimal to no AR experience. For each annotation, participants completed three 2-minute runs of each condition, and then were interviewed at the following end of the study to gauge how they perceive the annotations. So the results of the study found that sticky notes were beneficial for task performance as they resulted in more hostile eliminations than the control and icons, more hostiles engaged than the control and icons, more hostile eliminations than animations, icons, and the control, and more elimination EC, so elimination casualty, a higher elimination casualty ratio than the control. Sticky notes and icons and highlights also resulted in participants engaging lower threat levels than the control. And further to this, our subjective results found that participants felt that sticky notes, icons, and highlights were able to support their informed decision-making more than the control, and felt that sticky notes was helpful for reducing time pressure compared to the annotations of animations, highlights, icons, and the control. Furthermore, participants also felt that all the annotations were more helpful than the control in communicating information and supporting the memory recall. For preference, participants preferred the sticky notes, icons, and highlights over the control for supporting their performance and their decision-making. Did I jump? Oh, no. While our investigation showed that sticky notes is likely to be the most beneficial annotation out of the ones used, our interview with participants brought to light that reading text takes time, therefore a heavy text-based system may not be appropriate. And it was also noted that language barriers may exist, or language proficiency, or people suffering from any type of learning disorders may be impacted by sticky notes, and sticky notes may not be the best option there. So our second most likely annotation was the icons, as they're easy to understand and require less. They're easy to understand and quick to consume. Our results in combination with the participants' interview helped formulate several considerations to take into account when using annotations for time-critical tasks. Firstly, the time-critical environments may affect the consumption of the annotations due to the limited processing time. Therefore, annotations should be easy to recognize and convey information quickly, rather than being overly explicit. Secondly, was that the abstraction levels may affect the consumption of annotations, as annotations on the higher end of the spectrum, on the extreme end of the spectrum, can be difficult to parse, increasing consumption time. Therefore, in some cases, annotations should be lower on the abstraction spectrum to avoid comprehension issues. Thirdly, and lastly, was that visual complexity of an annotation can influence the understandability of it. However, when an operating environment requires realism, the more visually complex annotation is suitable, so in this case, animations. Conversely, when attention grabbing is the only thing of importance, the less visually complex annotations like highlights would be more suitable. Therefore, visual complexity must be tailored for the operating environment that they're being used in. And that is all. Thank you for listening.
Hey, thank you very much, Jamie. We definitely have time for questions, and we have only one hand.
Yeah, thanks for the presentation. Maybe two questions. So maybe the first one, if I understood it correctly, the annotations are displayed when gazed upon?
Yeah, so there's an area, I'll go back to the slide to make it a bit more. So those pink area circles represent an area of interest. So when the user, which we were using a HoloLens 2 for this, so when the user looked at the area of interest, then an annotation would spawn, depending on what condition they were running. And if they looked away, the annotation would still remain there, because obviously there would be an issue if it just disappeared straight away, because then you would have to constantly be looking at that one area. So they stayed there for a few seconds after looking at it as well.
What was your design rationale behind this? Because I would assume that in such a scenario, right, I mean, it's a strategy game. Essentially, I would like to know about the dangers that are all over the place, right? I would not like to just know about the dangers that I look at, but...
Okay, well, the reason for this is because so we worked with DST, so the Defense Department for this, and one of the things in military environments is that they're very complex, volatile, and uncertain, right? So you can't really assume that, hey, I know where every enemy is, or I know where every hostile is, or I know what's going to happen everywhere. That's why we use these pink discs, right? So before looking at them, you shouldn't really be aware what's there. So in a military case, right, you would know that something's happening at some point in time, right? Like, oh, some bad event has happened here, or there's something going on here, but you don't actually know what it is until you observe it, right? Does that answer your question, or did I segue into it?
It answers my question, but I still think, at least if there would be a very important threat, right, like close to my base, I think I would like to know about it, even if I don't look at it, but maybe that's a different topic. Maybe just one question. So in the use of the icons, right, you have the swords and then you have the danger above it, I think.
Ah, yes.
Did you consider combining different channels? Because here you have the visual channel encoding to some extent for icons the danger, but you are leaving out the color channel completely. Why is that?
So with the annotations, we tried to keep the color consistent between the annotations. So you'll notice the icons down the bottom is the swords with the red dots, which represent threat level, whereas the highlights is still red, and instead it uses rings to represent threat level. So the reason was just that we wanted the color to be consistent throughout all the annotations.
Okay, thank you.
Do we have any more questions? Okay, in that case, thank you very much, Jamie. All of our speakers, I think, are going to be sticking around afterwards, and any authors who weren't speaking, if there are any, because I think at least one author who was also speaking. So they'll be up there and delighted to go and answer your questions. Thank you.